You probably heard people say this about AI in a really dismissive way. Oh, it's just predicting the next word. They say it like that's an insult. Like it's supposed to make the whole thing less impressive. Um, and I want you to hold on to that phrase for a little while because by the end of this video, something interesting is going to happen. That sentence LLM are just next token predictor is going to go from sounding dismissive to sounding obvious. You're going to understand exactly why predicting the next word is enough to produce language, code, and also reasoning. And once you see it, you won't be able to unsee it. So here's the question for today. We build a neural network in video 4, right? A layer of math that takes number in and push numbers out. And we taught it to learn in video 5, like gradient descent, loss, and all that. But how do you take the math machine and make it speak English? How does a pile of matrix multiplication start writing poetry and debugging code? The answer turns out to be surprisingly simple. Let me show you how. Before I can explain anything, I want you to play a game with me. I'm going to show you a sentence with the last word missing, and all you have to do is guess what comes next. Ready? The cat sat on the. What word come to your mind? Don't overthink. Just say the first thing that pops into your head. You probably said mat, right? Maybe floor, maybe couch. And here is what I want you to notice. When I asked this question, what was going in your brain? Look at these options. Mat is almost like 62%. Floor is next to at 21%. Couch and table are trailing behind. And you didn't need to understand anything about cat or sitting or what a mat even is to get it this right? You just seen a sentence like this before, so you know which word tends to come next. That's it. That's the whole game. You look at what comes before and you guess what follow. And here's the thing that makes this so powerful. You don't need to teach meaning. You don't need to program grammar rules. You just need prediction. If something can play these guessing games well enough over and over on enough examples, language starts to emerge out of it. That's what language modeling is. Now, here's the obvious practical problem we need to deal with. Computer don't understand words. They just understand numbers. So if you want a neural network to play the prediction game, we first need to turn the language into something it can actually work with. And we do that in 3 steps. First, we tokenize. We break the text into smaller pieces. Usually words are part of the words. Then we embed. We turn each of these pieces of words into a vector, which is just a long list of numbers, an array of numbers. And then we feed those numbers into our neural network, which does its things. Let me show you how that actually look like. Take our sentence. The cat sat on the mat. Okay. We split it into 6 tokens, one per word, right? And then each token gets converted into a vector, a list of maybe 512, let's suppose, right? 512 numbers. So the word cat becomes something like 0.23, comma 0.87, comma 0.45, right? And so on. Hundreds of number that together represent what cat means in this space. This representation is called embedding. And here's the beautiful part. We don't program these numbers by hand. The network figure out what the numbers need to assign to each word during training. The embedding are learned, which mean they emerge naturally from predicting the task itself. So here's a mental model that makes this whole embedding idea really intuitive. Think of every word as a point floating in a space, like a dot on a map, except instead of two dimension, you got hundreds. And look at what happens when you actually plot these words out. King ends up near queen, and uh, and also prince, and sort of they're clustered together, right? Here you can see it in purple. Similarly, cat, dog, puppy. Similarly, Paris is near to France, right? You can actually drag these numbers around. These words around. If I put it here, it might feel a little bit out of context. Here, it might feel a little bit out of context. Here, it might not be that out of context. But this is the space where it feels most intuitive, right? But here's the distinction that really matters, right? King isn't near queen because the model understand what royalty is, right? It doesn't understand what royalty is. It's near queen because the sentence that contains word tend to look a lot like sentence that contains the word queen. The closeness come from the pattern in the text, not from the understanding of the concept in the words, right? Or there's no meaning that is is being understood here. That's a subtle difference, but it is an important one, and it's going to come back later when we talk about limitations. So here's something that surprises a lot of people when they really sit with it. The network isn't learning words, it's not memorizing definitions, nor building some internal dictionary. What it's actually learning is relationship, the way words relate to each other. And I mean all kind of relationship. It picks up that the adjective tends to come before noun. The verb usually follows their subject. The code has a consistent structure where function gets defined before they are called, and the brackets always come in pair, right? The maths follow its own set of patterns. All of these relationships, grammar, syntax, code structure, mathematical notations, the model discover all of them through one single task, just predicting the next token. We never programmed a single grammar rule. We never told it that verb follows subject. We just said, guess what comes next? Over and over, billions of times. And the grammar emerges on its own. Because here's the thing, you can't predict the next word accurately without implicitly learning these rules that governs how words are arranged. And the secret, if you can even call it a secret, the task is actually simple. Predict the next token. But the data is enormous, right? Trillions of words of human text. A simple task plus a simple task, that is predict the next word, right? And then there is enormous data, which equals to complex behavior. It learns the complex behavior. It's almost disappointing how straightforward it is once you see it. Let me show you the actual mechanism of how this works, because it connects directly back to what we covered in previous videos. During training, we take a sentence from our data. Say the cat sat on the mat. We hide the last word and give the model everything before it. So the input is the cat sat on the, that's it. And the target is the right answer that we know, mat. The model looks at the input, right? That is the cat sat on the, right? And makes its best guess at the next word. And then we check how far off it was, right? If it gets house instead of mat, that's a big error. If it gets rug, smaller one, right? Not that big a deal. And that error signals the loss. This is the same loss that we discussed in video 5, which tells the model in which direction we need to adjust the weight. So the loop looks like this. The model predict, we compare that prediction to the actual answer. We compute the loss. The weights get adjusted through gradient descent, and then we do the whole thing again with the next sentence. And we keep going. Not thousands of times, not even millions, but billions of times across trillions of tokens of text. And that's what come out of out the other end. You know, what come out on the other end is genuinely remarkable. Grammar emerges. Nobody programmed it. The model just discovered that certain words are ordered together. And if you predict them, that makes sense. Style emerges. The model learns that formal writing and casual texting follows the different pattern. Even reasoning emerges because the reasoning gets expressed through language. Language has a learnable structure. None of this was programmed in. It was all sculpted by prediction. Okay, here's a way to make you feel really concrete about this idea. You use autocomplete, right, on your phone. I think you use it every single day. You start typing a message and your keyboard suggests the next word. That's the exact same idea as a large language model. But look at the difference in the scale. Your phone autocomplete was trained on maybe few millions of text message. That little bar on the left, right? A large language model was trained on trillions of tokens. Books, article, website, code repositories, conversation, a huge chunk of everything human has ever written. That's enormous bar on the right. And that difference in scale is everything. The fundamental mechanism is identical between the two. Look at what comes before, predict what comes next. But the scale is completely different. Deep network, better optimization, and vastly more data. That was what LLM bring to the table. That's why your phone suggestion sounds good, while your LLM can actually write an essay. It's the same principle, but at just different scale. Now we arrive at a part that genuinely make people uncomfortable when they hear it for the first time. Because what I'm going to say sounds way too simpler to be true. Anything that can be expressed in language can be learned by predicting language. Just sit with that for a second. It sounds reductive. It sounds like it can't possibly be right. But think about what it's actually saying. Mathematical proofs, they are written in sequence of symbols and words. If you can predict valid proof steps, you can generate a proof. Okay, computer code, it just text with very strict syntax rule. If you can predict syntactically valid code, you can write program. Emotional expression, humans pour their feelings into words every single day. If you can predict how people express emotions, you can produce a text that resonate emotionally. All of this, proof, code, emotions, they all live in language. And if it lives in language, then predicting language can capture it. And the reason this works isn't because the model understands math or code or emotions. It works because humans express their understanding through text. And text is exactly what the model is trained on. So the model learns to produce output that looks like it came from someone who understands, even if there is no actual understanding underneath. Whether the gap matters is a fascinating question, but it's a philosophical one, right? The engineering reality is that predicting alone gets you remarkably far, right, in your approach to get the desired output. Now that we understand how this model works, we can also understand exactly where they break down. And this is important because knowing the mechanism tells you the failure mode. There are really two ways a language model can fail. First, if knowledge is simply isn't in the training data, if no human ever wrote it down, the model has never seen it, and it has no way to know it. You can't just predict what was never there to begin with. Okay. Second, if the language exists somewhere, if the knowledge exists somewhere, sorry, but isn't inferable from the pattern, right, in the text. Some things require real world experience, right? Some physical intuition, or kind of reasoning that doesn't leave trail in the written language. No amount of next work to no next word prediction will get you there. In both cases, model fails, and it's not a bug. It's working exactly as designed. It predicts based on pattern in the text. So when the text doesn't contain the answer, neither does the model. And this bridge us to the and this sorry brings us to the single most important distinction you can make about these systems. LLM knows what human tends to say, but that's not the same thing as knowing what's true. Human write things that are wrong all the time, confidently and frequently. The model learns from all of it, right? The accurate and the inaccurate alike. So when a LLM sound confident, that confidence is telling you this is what human typically say in this context. It's not telling you this is correct. Let me give you the last mental model to tie everything together, because I think it captures both the power and the limitation in a single image. Think of a language model as a massive echo chamber. It took in everything humans have written, trillions of words, and it compressed all of it into patterns. And when you prompt it, what you get back is an echo of humanity writing, blurred and probabilistic. That's what this flow look like. Human writing goes in one side, the training process extract the pattern and and process them into models weight. And when you ask it a question, you get back a probabilistic echo. The model best guess at what a human would say next based on everything it's observed. And this explains two things that confuses people about this model. First, brilliance and complete nonsense can come from the exact same system, like humans, because both were in the training data. The model learned from Shakespeare and from internet comments. It echoes all of it. Second, sounding confident doesn't mean being correct. The model isn't outputting truth, it's outputting the most probable next token. Sometimes probability and truth line up, and sometimes they don't. All right, let's make sure this all came together. If everything clicked the way I think it did, you should be able to say one sentence that means every word of it. A language model is a neural network trained to predict the next token in text after converting words into numerical representation. That's it. Word goes in as numbers. The network predict what comes next, right? And it's get better through training. That's a language model. If that sentence feels clean to you right now, not mysterious, not magical, but just straightforward and obvious, then we are in great shape. Because that means you actually understand the mechanism, and understanding the mechanism in this particular case is the whole point. Now, there's something I have been leaving out on purpose. Everything we talked about today, the prediction game, the embedding, the training loop, all of this works. But the early models that used this approach actually were not that good. They struggled with long sentences because by the time they got to the end, they already forgotten what was in the beginning. They had a real problem with memory and with understanding how distant words in a sentence relate to each other. And for a while the whole field was kind of stuck. The idea was right, but the architecture couldn't keep up. Then in 2017, some researchers, got together and came out with a paper that changed everything. It introduced a new architecture called transformer, and at its core was a mechanism called attention, a way for the model to look at every word in the input and decide which one matter most for predicting the next one. That's video 7. Why old model failed and how attention changed everything. That's where modern language model truly begins. And I'll see you there.